Hey guys, today we're going to have a look at something called the binomial distribution. Now, I reckon you can remember from last year we had a look at something called the binomial expansion, and we're going to have a look at how that relates a little bit later. But first of all, we just want to have a look at what we define the binomial distribution to be. And then we're going to have a look at probabilities of binomial distributions. Okay, let's have a little look. All right, a binomial distribution is created by running the Bernoulli trial a number of times. Now, remember what the Bernoulli trial was? There were only two outcomes, and the events were complementary. Okay. All right, so let's have a look at these. Right, the first event is getting the number of tails when tossing a coin 6 times. Okay, so the first thing we have a look at, are we dealing with multiple trials? We're tossing a coin 6 times. So we have multiple trials. Multiple trials. Okay. Second thing is, are there only 2 outcomes, and are they complementary? So what are our outcomes when we are tossing a coin? Our outcomes are heads and tails. And are they complementary? Probability of getting a head is a half, probability of getting a tail is a half. Yes. So in this situation, looking at getting the number of tails when tossing a coin 6 times is absolutely a binomial distribution. All right. Having a look at the next one. Getting the number of picture cards from a deck when 5 cards are drawn. Okay, so let's have a look. Are there repeated trials? So we have a deck of cards and we are drawing 5 cards. All right, and we are having a look at the outcome of getting a picture card. If we have the outcome getting a picture, what is the complementary outcome? The other outcome is not getting a picture. Okay. Now, I haven't written down here, but in this case, we are drawing 1 card out and replacing that before we draw it out. So we have the same number of cards we're drawing from each time. Okay, so there's only 2 outcomes. They are complementary. And there are 5 repeated outcomes. So that is an example of a binomial distribution. So let's have a look here. So in theory, to test a binomial distribution, we have a fixed number of trials. So whether it happens twice, 5 times, we know how many times the event is happening. Each trial is independent. In other words, whatever I get on the first trial has no bearing on the second trial, and so on. Okay. Third, the 2 outcomes are complementary. That's part of the Bernoulli distribution. So you've got probability of getting P and 1 minus P. Okay, 2 outcomes, complementary. There we go. And the probabilities are the same each trial. In other words, the probability in trial 1 of getting a certain outcome is the same as the probability of getting that outcome in trial 10. Okay, the probabilities do not change as the number of trials change. Okay, so let's have a little look here. Let's go through our checklist. 1, 2, 3, 4. Okay, there are a fixed number of trials. So we have the number of odd numbers when rolling a dice 20 times. Okay, so what is the trial that's happening here? We are rolling a dice 20 times. So we have 20 trials. That's a fixed number of trials. So tick, tick, first one's done. Each trial is independent. So we've got to ask ourselves here, is the probability of getting an odd number on the first roll of the dice the same as on the 8th roll of the dice, the 10th, or the 20th roll of the dice? Yes, it is. Okay, so each trial is independent. The 5th trial has no bearing on what you're going to get on the 20th trial. So tick, tick. All right, two outcomes are complementary. Right, so we either get an odd number or not an odd number, okay? Or an even number if you want to call. And, of course, odd number, not an odd number are complementary events because you can only either have an odd or a not odd number. So, tick, tick. Complementary outcomes. And the probabilities that are the same each trial. So, the chance that I roll an odd number on the first trial is the same as rolling an odd number on the 10th trial. Okay, so same probabilities. Okay, so tick, tick. So that tells us that this is an example, let's go hot pink, of a binomial distribution. Okay, let's look at the next one. Okay. Selecting 5 black cards from a standard deck. Standard deck is the 52 cards. And not replacing the card after each draw. Okay, so let's go through our little checklist. Do we have a fixed number of trials? How many trials is happening here? We are choosing 5 cards. We happen to want 5 black cards. So here there are 5 trials. Fixed number of trials is not 8. There's not indefinite. There's 5. Okay. Second thing is, are they independent? Okay, so I'm going to highlight this here. It says not replacing the card after each draw. So after the first draw, I leave it out. So on the first draw, I have 52 cards. And you can work out the probability. What about on the second draw? If you do not replace a card, you'll have 51 cards. What does that do to the probability? It changes it. Okay? So what you get on the first draw directly affects what you can get on the second draw. So if I draw out a black card in the first draw, there's now less black cards in, so the chance of getting a red card increases. So it is not independent. Not independent. Okay, so first cross there. Let's have a look at the next one. Are they complementary? So we either get a black card or a red card. There's no other options. Every card is either black or red. So they are complementary. And lastly, the probabilities of each trial is the same. Well, as we mentioned up here, what's the probability of getting a black on the first trial? That is 26 out of 52. Let's say I drew a black on the first trial. What's the probability of getting a black on the second trial? There's one less black, so there's only 25 blacks. There's one less card, 51 cards. So the probabilities are different each trial. Different probs. So in this case, because of the not independence and the probabilities changing each time, that one is not an example of binomial probability. Okay, so let's go have a look at our next sec. Our binomial probabilities. We're going to do an example here. We're going to model it the way we normally would do a question like this, and we're going to have a look at some shortcuts later on. So here we've got a question. A card is drawn from these 4 cards. So we've got a number card. This is a number. And these 3 here are non-numbers. Okay. So you either get a number card or you get a not number card. Okay. So we're drawing 3 cards. 3 cards are drawn. So we have 3 trials. Okay. And then replace. So when we draw a card, here's the key thing. Draw a card and then they're replaced. So every time we draw a card, you'll still have the same 4 cards there, as opposed to what we looked at where there was no replacement. All right, so if we go through determining if it's binomial probability, they are complementary outcomes, number or non-number. They are independent. Chance that I get a number on the first draw is the same as getting a number on the 4th draw. They are, what am I looking at here? The probabilities are the same each trial, and the two outcomes are complementary. So this is an example of binomial probability. Okay, so we can now have a look at how we might do this. So 3 cards are drawn. So we have a multiple event happening. Okay, if we remember back, probably one of the most common ways of looking at this is looking at a tree diagram. So let's draw a tree diagram for our 3 draws. First draw. We either get a number or not a number. Second draw. If we get a number first, we can get a number second, or we can get not a number. Or if you get not a number first, you can get a number or not a number second. And the third draw. Number, not number, number, not number, number or not number, number and not number. Okay, so let's go and list our sample space. So we've got number, 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 not number, number, not number, 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 not number, not number. There we go. There's the first one. Let's do the next one. Not number, number, number. It's very annoying if the numbers are not. Not number, not number, number, and not number, not number, not number. Okay, so we have 8 outcomes. However, the outcomes are not the same. So let's go and have a look at what we normally do here. We put the probabilities on the branches. Okay, so probability of getting not a number first, getting a number is 1 out of 4. Not a number is 3 out of 4. Once again, 1 out of 4. This is where the probabilities are the same. 1/4 here, 1/4 there, because we're replacing the cards. 3/4, 1/4, 3/4, and so on. And I'll just put over here 1/4, 3/4. Okay, I haven't finished filling those in, but that's okay. All right, so let's now have a look. Probability of getting no number card. Okay, so let's have a look what we want to do here. I'm going to do it over here. So A, probability of no number means no number, no number, no number. Well, if we have a look at that, here is the only outcome there. So that is 3/4 times 3/4 times 3/4, or 3/4 to the power 3. All right, and you can work that out, but we're looking for some patterns here. Okay, let's do the second one. Probably 1 number card. Okay, so let's have a look at the outcomes. So 1 number card is going to be, let's have a look at the first one. 1 number card would be this one here, that one there, and that one there. So we can have number, non, or no number, number, no number, or no number, no number, number. Okay. All right, so let's have a look at those outcomes. We've got no number, which is a 1/4, so that's 1/4 times 3/4 times 3/4. And when it's an or, we add, don't we? So plus 3/4 times 1/4 times 3/4 plus 3/4 times 3/4 times 1/4. Okay, I'm just going to neaten that up a little bit. All those brackets are exactly the same. The orders are just different. So we've actually got 3 of those, 3 lots of 1/4 and then times 3/4 squared. Okay, and you can work that math out. I'm not going to do that. We're looking for patterns. Okay, let's do the next one. C. 2 number cards. So let's look for the 2 number cards. So 2 ends. There's one there. There's one there. There's one there. And I think that's it, isn't it? Okay. So once again, probability of 2 numbers. using the approach we had above, it's going to be 1/4 times 1/4 times 3/4. And you're going to have 3 of those, aren't you? So that is going to be 3 lots of 1/4 squared times 3/4. Okay. And our last one, D. I'll do D over here. 3 number cards, probably of 3 numbers, number. Well, I think that's obvious. There's only one of those, just like there was only one of 3 not numbers. So what have we got? We've got 1/4 to the power 3. Okay. All right, you can work those probabilities out. You've done plenty of that before. I'm just going to put them in a row, and I want you to have a think about where you may have seen these here. Okay, so 3/4 to the power 3. 3 times 1/4 times 3/4 squared. 3 times 1/4 squared times 3/4. And 1/4 to the power 3. So let's highlight a couple of things. 3, 1, 1. So 1 and 2, 2 and 1. And if I want, I'm going to put a coefficient there and a coefficient there. So you may have seen things like this before. 1, 3, 3, 1. You may recognise that from somewhere. Okay. Right now, all I'd like to do is get you to finish this question here. What about if we had 5 cards selected? Could you work out the probability of getting 2 number cards? So you can either go and draw a tree diagram, or could you perhaps use some of these shortcut ideas that we have just found above? Okay, I'm going to leave a few questions for you to do just on this basic stuff, and we'll get together and have a chat about our findings next lesson. Bye.